Okay, so hello everyone. My name is Lohit Koyal, and this is the fourth live session of Introduction to Interfacial Labs. So let me share my screen and we can start. So today we will talk about perturbation technique. So in the last class, I have introduced what is perturbation technique. So let's do a small recap. So suppose you have an equation like this: x square minus 5x plus 6 equal to 0, and you know the solution will be x equal to 2, x equal to 3. Now, perturbation means small changes. So, how to interpret this? Suppose so. This is your equation, right? Now, if your equation is 5.002, sorry. So, if your equation is x square minus 5.002 x plus 6.004 equal to 0. Now, you are told to find the solution for this. Okay. Now, what you can always do, you can just apply the formula and find the solution. But suppose if we don't do that, okay, so how we can write this? We can write this in this way: x square minus 5 plus epsilon x plus 6 plus 2 epsilon equal to 0, where epsilon equal to 0.002. Now you are told that you have to solve this using this. So you already know the formula for x square, the solution for x square minus 5x plus 6 equal to 0, and you are told to find the solution for this equation, using this 2 and 3. These two are your solution. Okay, so let's try to do that. So as you know that for the perturbation expansion, what we will do, we will expand x like this: x equal to x naught plus epsilon x1. Okay, so this is plus order epsilon squared. So we are truncating it up to order epsilon. Okay. So now what we will do? So I am saying that this is a solution. So what I have to do? I have to substitute it here. So if I do the substitution, I will get x naught square plus 2 epsilon x naught x1. So remember that we are not interested in the order epsilon square terms. Okay. Minus 5 plus epsilon x naught plus epsilon x1 plus 6 plus 2 epsilon equal to 0. This implies, so what will be the result? So now I will separate order 1 solution and order epsilon solution. So what will be the order epsilon, order 1 solution? Order 1 solution you already know. Order 1 solution is x, or the first, let us find the equation, then we'll find the solution. X naught square minus 5 x naught plus 6 equal to 0. You see that this is the order 1 solution. You know already know the solution x naught equal to 2 and 3. Now what will happen at the order epsilon? We will have 2 x naught x1 minus 5 x naught 5x1 minus x naught plus 2 is equal to 0. So at order 1 you will get this result. So now we already know the expression for x naught, right? So we need to write x1 in terms of x naught. So how can we do that? It will be x1 if we take common x1 from these two terms. So we will get 2x naught minus 5 equal to 2 minus x naught. So it will be x1 equal to 2 minus x naught by 2x naught minus 5. So this is a quadratic equation. So we have two base-state solution. Remember that order 1 is the base state. So we have two base-state solutions. So you will have 2x1. So case 1, when your x naught is equal to 2. So you can clearly see that x1 is strictly 0. X not equal to 2, so it is 0. Case 2, x not equal to 3, and x1 will be 2 minus 3 divided by 2 into 3 is 6 minus 5 is equal to minus 1. So what will be your solution? Your x will be equal to 2 and 3 minus epsilon. So and what is epsilon? Epsilon is equal to 0.002. Now if you substituted this equation in this expression, you can see so if you substitute these solutions in this equation, you can see that your solution is reasonably correct up to some order. Okay. Now, if you want more accurate answer, you can always write epsilon squared x2 plus epsilon cube x3, etc. If you expand this in this way, then your solution will get more and more accurate. So this is the basic idea of the perturbation technique. So we have done it so far. Now we will try to implement this in some differential equation. Okay. So let us first. So I will use exactly the same thing in the differential equation. Okay, nothing else. So suppose you have equation like this: d2x dt square plus x plus epsilon x square equal to 0. So I will use exactly the same idea. So x equal to x naught plus epsilon x1. This is my basic expansion. Okay. Now let us substitute that. Okay. So what we will have? We will have d square x naught dt square plus epsilon d square x1 dt square plus x naught plus epsilon x1 plus epsilon x naught plus epsilon x1 whole square equal to 0. So remember that we have taken our expansion up to ordered epsilon. So we need the solution up to, so we will consider term here to order epsilon. Okay. Okay. So now let us write down the order 1 solution. So it will be d square x naught dt square plus x naught equal to 0. Order epsilon, it will be d square x1 dt square plus x1 plus x naught square, right? Now remember that here x1 is unknown, but by that time x naught is already known, so you can easily solve this equation. So what is the solution? Tell you. So what is the solution for this equation? X naught t is sum a cos t plus b sin t. Okay, we can specify some initial condition, but that is not. But for now, let's just keep it general. Okay. Now, what we can do, we can easily substitute it here and find a solution. So what will be the solution? It will be d square x1 dt square plus x1. So we will substitute this x naught here, okay, minus a cos t plus b sin t whole square equal to 0. This implies this equal to a square by 2 1 plus cos 2t. So I am taking it to the right hand side, okay? Plus b square by 2 1 minus cos 2t plus ab sin 2t, okay, equal to a square plus b square by 2 plus a square minus b square by 2 cosine of 2t plus ab sin 2t. Okay, so now what kind of equation is this? This is a this is a linear and non-homogeneous equation. And for non-homogeneous equation, we will have a complementary function and a particular integral. Okay. Now see this equation on the left hand side, and let me give it another color. This equation and this equation. So on the left hand side, they are the same. Okay, only the right hand side is different. So its complementary function will be again some c1 cos t plus d1 plus d1 sin t. So it will not improve this solution. It will get improved by a little. So it will be a plus epsilon into c1 cos t plus b plus epsilon d1 into sin t. Okay, that's all. But as epsilon is a small parameter, so the change will be small. So we can do what we can do. We can simply take the particular integral. Okay, so if we just take the particular integral, then what will happen? Remember that we can neglect this complementary function because we are not bothering about initial condition. If we specify some initial condition, then to satisfy the initial condition, we need to consider both complementary function and the particular integral. But here, as we are not specifying any initial condition, we can keep it general. So we can, for this time being, we can neglect this complementary function. Okay, but remember that when you are calculating, it is always good to calculate both, because otherwise your initial condition will not be satisfied. Okay, so let us calculate a particular integral. so how can you, so you know that you can use them, you can use various techniques. One method is method of undetermined coefficients, or variation of parameter. You can use anything, or a green function. So undetermined coefficient is the simplest technique. So what we can take, x1 equal to some constant, maybe this alpha plus beta of cos 2t plus gamma, this is gamma, okay, of sine 2t. I am assuming it. Remember that this is pi only, not cf. So now what we have to do, we have to just substitute it. After substitution, we will get alpha plus, it will be alpha minus 3 beta cos 2t, because d square, because if we take the double derivative, it will be minus 4 beta, and here it will be beta. So it is minus 3 beta cos 2t minus 3 gamma sine 2t equal to what we have on the right hand side. It is a square plus b square by 2 plus a square minus b square by 2 cosine of 2t plus ab sine of 2t. So if you compare the coefficients, you will get alpha equal to a square plus b square by 2, beta equal to minus of a square minus b square by 6, and gamma equal to minus ab by 3. Okay. So what is your final expression? So you will have x naught equal to a cos t plus b sin t, and x1 equal to, so remember this is pi only, it is a square plus b square by 2 minus a square minus b square by 6 cos 2t minus ab by 3 sin 2t, and your entire solution is x naught plus epsilon x1. So this is your entire solution for a system like this. Okay, done. Now, just if I just change the equation a little bit, if I change it to, instead of epsilon x square, if I change it to epsilon x cube, then what will happen? Just try that. So now our concerning equation is d2x dt square plus x plus epsilon of x cube. So the entire procedure will be same. Okay, x equal to x naught plus epsilon x1, and we will do the same procedure. So what we will get at x naught, I will get a cos t plus b sin t. Okay, and what will happen at the third order? At the third order, first let me write down the equation: d square x1 dt square plus x1 equal to minus epsilon x naught cube. Just follow the same procedure like I did in the last question, and you will get this answer. I mean, you will get this equation. So now for this time being, let us just don't bother about the cosine of t. Okay, we want to keep this thing simple. So let's just work with a cos t. So it will be minus epsilon. Okay, so now epsilon will not be here, only x naught cube, because this is anyway in order epsilon. So it will be minus a cube cos cube of t. And now what is cos cube of t? Just use your your knowledge about trigonometry. It will be, I think, cosine of 3t plus 3 of cosine t. Okay. Now, in the last question, where you have epsilon x square, the perturbation method works well. There was no problem in this equation. But can you see a problem here? See that the left hand side is anyway the same. Left hand side is same. It has the solution of x1 of cosine t. Okay, it's something cosine t or sine t. But on the right hand side, we get a term of cosine t. Okay, now suppose you have an equation of d square y dt square plus y equal to some sine t. Do you know what is the solution of this equation? The solution of this equation will be either t cos t or t sine t. Let's try that. Let us just take a equal to a into t cos t plus b into t sine t. And let us just do the substitution. So first dy dt, it will be ta into cos t minus t sine t plus b sine t plus t cos t. Now do dy dt square. It will be a into minus of sine t minus sine t minus t cosine t plus b cos t plus cos t minus t sine t. So it will be a into minus 2 sine t minus t of cosine t plus b into 2 cosine of t minus t sine t. Now your equation is d2y dt square plus y equal to sine t. And you have taken your assumption as y equal to a t cos t plus b t sine t. Now just do the substitution. If you do it, you will get finally minus 2a sine t plus 2b cos t. Other things will get cancelled is equal to sine of t. If you do the comparison, you will get a equal to minus half and b equal to 0. So your solution of this equation, the particular integral solution is equal to minus of half t cosine of t. Okay. So what happens here? So when t tends to, so now what is the curve of t or the t cos t? The curve of t cos t is something like this. This is some y equal to t, something like that. Okay. So as t increases, remember that cos t will take value from +1 to -1. Okay. So it is oscillatory. But as t increases, so the amplitude of the oscillation will continuously increase, which indicates that this solution is unstable. Okay. Now, now see this equation. Now, you can verify. You can very easily solve it numerically. Just use MATLAB, Mathematica, anything. You can verify. You will see that this gives you a periodic solution. It gives you a periodic solution. Okay. Or you can from your intuition you can say that this is d2s dt square plus x is give you a periodic solution, right? And you are just increasing it by a small amount. Okay, this is some small kind of error. You can think like that. Okay, your epsilon is very small term, 0.001 maybe into x cube. So anyway the scenario will be periodic solution. Okay. But what does your perturbation technique do? Your perturbation technique predict that there will be unstable solution. If you solve this, you have a solution like t sine t or t cos t, right? But which is unphysical. Okay, but there is no such phenomena in your physics. There is no such phenomena in your governing equation. But the perturbation technique that you have chosen, it is giving you wrong answer. So that means this perturbation technique is wrong for this problem. Okay, that's why we will use two new different perturbation technique. Obviously, this is a perturbation problem, so we have to use perturbation technique, but we will use two new different technique that you have already learned about it. That is lead state Poincare and multiple scale. Okay, so now in the lean state Poincare technique, what we do, we just stretch the time. We define a time 1 plus some epsilon into omega. We define our time like this. This is our original time that we are governing, that we in our equation, and we are stretching the time. Okay, this is my lean state Poincare technique. And in the multiple scale technique, we define a slow time scale. So if my original time scale is t that we are using, and we define a slow time scale in this form of epsilon t or t2 equal to epsilon square t, something like that. Now we can solve it. Now suppose in this equation, if we solve it in this using this lean state Poincare technique, let's see what can happen. So now, so I will do this problem, that is d square x dt square plus x plus epsilon x cube equal to 0. I will solve this equation. Okay. Now I will not use this time t, I will use instead of that, I will use t into 1 plus epsilon sigma. Okay. Now what? Now we need to do some other. So we need to so basically we need to modify this d2x dt square, right? So how can we do that? So we will use the chain rule, d of d tau into d tau dt, right? So it will be 1 plus epsilon sigma d d tau. So and d square. So d square dt square, it will be 1 plus 2 epsilon sigma d square d tau square. Why 2 epsilon sigma? Because I will just do 1 plus epsilon 1 epsilon into epsilon sigma whole square. But we are neglecting the order epsilon square term, so it will be 1 plus 2 epsilon sigma d square d tau square. Okay. So now what will be our solution at the base state? Our base state solution will be d square x naught d tau square plus x naught equal to 0. So remember, so I am just taking a into cos term. This is not the complete solution, but for the simplicity, I just want you to show that this method will work for this problem, this Lane state Poincare method. A cos term I am just taking, but originally you should have you have to take b sin term as well. Now the second order solution, we will have d square x1 d tau square plus x1, right? This is a simple case, but there will be one there is one additional term, that is x naught cube, that is in order epsilon. But remember, there will be one more term here, because that is coming from this term. So that will be plus 2 sigma d square x naught d tau square equal to 0. So now you will have d square x1 d tau square plus x1 equal to minus x naught cube minus 2 sigma d square x naught d tau square. So it will be minus of a cube by 4 cos theta. We have already done it, so I am writing down the final expression, plus 3 of cos tau, not t. This is tau, okay? Minus 2 sigma d square x, and x naught is a cos tau. It is minus a cos tau. So it is minus a cube by 4 cos 3 tau minus 3a cube by 4 cos tau plus 2 sigma a cos tau. Okay. Now see the left hand side and right hand side. So remember that to get a physical answer, we need to remove this anything related to cosine of t. But in the previous method, we didn't have any mechanism. We didn't know how to remove this term. But here, as we have stretched our time, we have a coefficient, and we can modify and we can tweak the coefficient to make the cosine the coefficient at our coefficient before cosine is 0. So if we do that, we will get 2 sigma epsilon minus 3 a cube by 4 equal to 0. This is our agenda. That means 2 sigma epsilon minus 3 a cube by 4 equal to 0. So sigma equal to 3 a square by 8. So what will be your modified time? Your modified time tau will be t into 1 plus epsilon into 3a square by 8. Okay. Now when you have removed this term, what you are only left with this term. You are only left with d square x1 t tau square plus x1 equal to minus 3a cube by, sorry, minus a cube by 4 cos 3 tau, because we have already removed the cosine term and we can solve it very easily. All right. So this is the power. So this is the, and if you do the complete calculation, I'm not doing it here. If you do the complete calculation and compare it in numerical result, you will find a very good agreement. Okay. So similarly, using so now your multiple scale technique is a more powerful technique than this Lindstedt Poincare technique. Suppose you have some viscosity as well in your system, some damping term, then you will see that your Lindstedt Poincare technique will not work. There you need to use your multiple scale technique. Okay. Okay. So this is the brief introduction of the perturbation technique. Now we can go and solve some problems. Okay. Right. So let us solve. Let us solve some assignment problems. Okay. The first question in the fourth assignment. Okay. So solution. Right. Yeah. Just give me a moment. Okay. So the first question says that you have a equation like this: x double dot plus gamma x dot plus omega 0 square x equal to f0 sine omega d t. Okay. Now you need to find a general solution when 4 omega square is greater than gamma square. Hmm. Okay. So now okay. So now, so how you can solve this problem? Okay, so this is the linear equation, so you can solve this problem very easily. So simply substitute x equal to e to the power mt. So we will get m square plus gamma. So first, so let us solve the complementary function, then we will solve the particular integral. Gamma m plus omega 0 square equal to 0. So your m equal to minus gamma plus minus of gamma square minus 4 omega naught square divided by 2. Now it is provided that 4 omega naught square is greater than gamma square. So it will be minus gamma by 2 plus minus of I this is the iota, 4 omega naught square minus gamma gamma square. So what is the general solution for the complementary function? It will be, so xt equal to a into e to the power minus gamma t by 2 times a cos square root of 4 omega naught square minus gamma square by 2 t plus b sine omega naught square minus gamma square by 2 t. All right. Now, suppose you have a suppose you have equation like this. Mm, you have equation like some a cos. Okay, so you have something a into cos something t, b into sines into something t. Now we can simplify it. So it is given that omega square equal to omega 0 square minus gamma square by 4. So just see that if I take this 4 outside, it will be 2. So it will be gamma square by 4. So and 2 will cancel. So it is nothing but omega itself. Okay. So we can write at xt equal to e to the power minus gamma t by 2 a cos omega t plus b sine of omega t. Okay. Now you have, if you have some equation something like this. Now I can write r equal to some cos delta, r into cos delta. No, let us write a equal to r into some sine delta and b equal to minus r sine delta. Now, what is a and b? It is still not known to us. So, how can we get it? It will definitely come from the initial condition, which is not provided because you are finding the general solution. So, if we just substitute that. Okay, but let us do one thing. This is your, okay. So we can do it differently. So this is your complementary function. Okay. Now, what a particular integral. So what will be the solution of your particular integral? Mm, okay, I think the option is provided is something wrong in the assignment. Okay, so yeah, so let us just keep it here and let's try to solve what is the solution of the particular integral. Okay, so now if you substitute this, so on the right hand side, what you have, your f0 into sine into omega d t. Okay, so this is your on the right hand side. So your solution x of pi t, it will be something related to uh, alpha into sine omega d t plus beta cos omega dt. This is coming from the method of undetermined coefficient. Okay, just revise that. You will find it. Now, if I just substitute it here in this equation, what we will get? We will get minus alpha omega d square sine omega dt minus beta omega d square cos omega d t plus gamma alpha omega d cos omega d t minus gamma beta omega d sine omega d t plus omega 0 square sine omega d t plus omega 0 square cosine of omega d t alpha beta is equal to f naught sine omega d t. So this implies, so let us, we need to now separate the coefficients of sine omega d and cos omega d. It will be sine omega d t minus alpha omega d square minus gamma beta omega d plus alpha omega 0 square plus cosine of omega d t is minus beta omega d square plus gamma alpha omega d plus omega 0 square beta is equal to f naught sine omega d t. So what we get? We get that alpha omega 0 square minus omega d square minus gamma beta omega d is equal to f naught and beta omega 0 square minus omega d square plus gamma alpha omega d equal to 0. So from this equation we can get a relation between alpha and beta. So this we can take beta equal to minus gamma omega d divided by omega 0 square minus omega d square into alpha, and we can substitute it and we will get omega 0 square minus omega d square plus gamma omega d whole square by omega 0 square minus omega d square alpha equal to f naught. So your alpha will be f naught omega 0 square minus omega d square divided by omega 0 square minus omega d square whole square plus gamma omega d square, and beta will be equal to, beta will come from this equation, it will be minus gamma omega d f naught omega 0 square minus omega d square plus gamma omega d whole square. So and we have taken that xpi of t is equal to alpha sine omega dt plus beta cos omega d t. Now see, now if you look at the options that is given in the first question of assignment 4, you will find that this is my complementary function, that it is given, so it is a cos omega t and b sine omega t. Okay, now we can, how we can write a, we can write a equal to some r cos phi and b equal to r sine phi. Okay, so it is, so it will be what, some r into cos phi cos omega t, r into sine phi sine omega t. What will be r? R will be your simply a square plus b square, and phi will be your tan inverse b by a. So as a result, you can write it some constant. Some constant may be the some constant b, or in b prime. In the option it is given as b. It will be, the solution will be e to the power minus gamma t by 2 cos Yeah, extremely sorry that I did not realize that I got disconnected. So yeah, so I don't know where the connection got lost, but yeah, so but I have done the derivation and I will share it with you so you can see it. Okay. Now let us move on to the next question. The next question is an interesting question. Just a moment. Right. So now, suppose you have a system like this, okay? Then what will be your time signal? If you plot x versus t, then what will be your time signal? Now see, there are three different aspects to this problem. First is, let us modify this question a little. I mean, in step by step. Suppose you have an equation like this: d2x dt square plus x equal to 0. We all know what is the solution of this. It is either cosine t or sine t. Okay. Now, if we draw its a time signal, it will be something like this with a periodic solution. Pardon my drawing, but this is the sine t, or this is sine t. Now, if I add viscosity damping term to it, gamma dx dt plus x equal to 0. So, what will be the solution? Its amplitude will decrease and it will finally be 0. We know that, right? And now in this question, we have both damping and forcing. Now, if you don't have any damping, then what can happen? If you now don't have damping, okay, now forward, okay, or you can take damping. It will not matter. So if you put damping, there will be competition between damping and forcing. Which one is stronger? Okay. Now, if both of them are comparable, then what will happen? So what will happen? Initially, the system will behave in some bizarre manner, okay, some chaotic signal. But after when it will get a resonance, you can just think physically, okay. When it get resonance, it will just oscillate with this frequency, right? So after that, it will eventually get a sinusoidal signal. So it will have some initial transient period. This is called a transient phase, and this is oscillatory phase, right? So this is a kind of solution. This initially there will be uh, some transient signal, some bizarre signal, and later it will be a simple sinusoidal oscillation. Okay. Okay, now let's go to the next question. Huh. So here in the third question, you are given a nonlinear problem. So here you are provided your tau equal to omega 0 t and y equal to omega 0 square x by f0. Now here you need to find the expression for this equation. So if you now convert this equation to this equation, d2y d tau square plus 2 eta dy d tau plus y plus epsilon y cube equal to sine of sigma t, where eta, epsilon, sigma are some non-dimensional number now, but what are those? Okay, so you are provided everything and you need to find this expression. Okay. So, so now we can write t equal to tau by omega naught and x equal to y f naught by omega naught square. we can put this and substitute in this equation. Okay, so what will we get? We will get that f naught by omega square. So this is coming from the x part into omega naught square. This is coming from t d2y d tau square. This will be the first term. That is the d2x dt square plus gamma omega naught into this omega naught is coming from this t because this is in denominator. So 1 by dt. So omega naught will go to the numerator into f naught by omega naught square dy d tau plus x, that will be f naught y, plus epsilon cube plus epsilon into y cube. So it will be beta f naught cube by omega 0 to the power 6 into y cube equal to sine omega d into t. Instead of t, we will write omega d by omega naught tau. So we have got our first non-dimensional constant sigma. So we can just write sigma equal to omega d by omega naught. Now from here it will get cancelled. F naught d2y d tau square plus gamma f naught by omega naught dy d tau plus f naught y plus beta f naught cube omega naught to the power 6 y cube. F naught is multiplied here equal to f naught sine sigma tau. Now you can divide both sides by f naught, so it will be d2y d tau square plus gamma by omega naught dy d tau plus y plus beta f naught square by omega naught to the power 6 y cube equal to sine omega tau. Now if you compare with this expression, you will find that your eta equal to gamma by 2 omega naught and epsilon equal to beta f naught square by omega naught to the power 6. Okay, so the very just straightforward. You just write down the expression and just substitute it. Okay. Now the next one is the conceptual question regarding the multiple scale technique. The question says that in the multiple scale technique, option 1, an ODE is converted to an algebraic equation. Option 2, an PD is converted to an ODE. Option 3, an ODE is converted to a PDE, and the option 4 is nonlinear equation is solved analytically. Okay. So the correct option is an ODE is converted to PD, and how we will see it in a moment. Okay, so we will solve the equation using multiple scale techniques. So we have already solved equation using the ordinary perturbation technique, instant Poincare technique. Now this is the first time we will solve multiple scale technique. Okay, so let's go. So this is question number 5. Okay. So this is your equation: x double dot plus x square equal to 0. Okay. So we can take the perturbation like this: x equal to epsilon x naught t naught t1 square x1. Sorry, this is not x naught, this is x1, this is x2 t naught t2. Okay, so you can just do some substitution here, but remember one important thing. Now here d dt equal to del t naught del t naught dt naught dt plus del t1 dt1 dt. Your t not equal to t1 equal to epsilon t. Okay, so it will be del t naught plus epsilon del t1. So your d square dt square will be simply the square of this del t naught plus epsilon square. Now if we are interested in truncating at order epsilon, so it will be del square del t naught square plus 2 epsilon del square del t naught del t1. Now see that you have one variable originally t. From t you have converted it to t naught and t1. So what was originally your ordinary differential equation d of dt? You have changed it to a partial differential equation. Okay, all right. So now this is your equation. So what is the equation? So what will be the so let us just substitute that. Substitute everything. It will be del square del t naught square plus 2 epsilon uh, mhm, del square del t0 del t1 epsilon x1 plus epsilon square x2. So plus epsilon square del t1 square. So plus x naught plus x epsilon x1 plus epsilon square x2 plus epsilon x1 plus epsilon square x2 whole square equal to 0. Now at order epsilon, what is the equation? Del square x1 del t0 square plus x1 is equal to 0. So x1 is your sum a1 of t1, right? So we see that this is x1 is a function of both t0 and t1, and this is a partial differential equation of t0 only. So therefore, so the constant term, it will be a function of t1 into e to the power of I t naught plus some complex conjugate. Okay. Now at the second order, what we will have? We will have order epsilon square del square x2 del t naught square plus x2, and we will have something on the right hand side. It will be, it's one term will come from here, obviously. It will be minus x1 square, and another term will come from this minus 2 del square x1 del t1 del t0. This will be your another term. So now let's just do the calculation on the right hand side. So you are told to find what is the what is the correct function of a1. Okay, so you are provided four options. So what is the correct choice of this thing? And so let's just do that. So it will be minus x1 square and into this term. So it will be minus a square. Remember that a is a function of t1. E to the power. So I have this expression. So I am just now writing the right hand side only. Okay. E to the power 2y t naught minus 2 del a del t1 into I t naught into e to the power of I t naught plus some cc. Now remember that this term is a secular term. Okay, because this term is similar to the cos t and sin t on the right hand side that I have told earlier. Okay, so we need to remove this term, so the coefficient that is associated with this term has to be 0. So we can see that only coefficient associated with e to the power I t naught is del a del t1. So del a del t1 has to be 0. So that means what? A is not a function of t1. So a can be some constant. A is not a function of t naught, we know that. But also here we find that a is not a function of t1 as well. So thus it means that a is just a constant. Okay, then we can find the solution. Okay, so a is just a constant, we can just simply find the solution. Okay, so alternately it says you another thing. See that if a is just simply a constant, not any function of t1, see, it is essentially saying you that you can very easily apply your ordinary perturbation technique. Remember that we have solved a similar kind of problem in the kind of problem in the beginning. Okay, there we had epsilon x square, something like that, right? We had a problem like epsilon x square. If I do, yeah, we have a problem exactly similar problem like this. Okay, instead of epsilon x square, we have here x square only. But here x square means initially if you have your cos t naught, you at the second order you are getting cos 2 t naught. Okay, but that is not a secular term. So you are in luck. So that is not causing any problem. But if you have x cube, then you are getting cos t naught at the right hand side. So you need to use this Lindstedt Poincare technique or multiple scale technique. Here using multiple scale technique useless, but it is just for practice, right? Because it is useless because it is just saying you that your a1, this constant a that you have taken, that you have that you initially thought that it is a function of t1, you are just finding out that it is just a simple constant. So it is essentially saying that you can use ordinary perturbation technique as well. Okay, okay, now, okay, so question 6 also a conceptual one. Okay, so question 6 is also a conceptual question. It says that uh, using which perturbation technique can you obtain a consistent perturbative approximation to the solution of a damped harmonic oscillator equation? Okay. Option 1 is Lindstedt Poincare technique. Option 2 is multiple scale technique. Option 3 is the regular perturbation technique, and option 3 is none of the method, none of the above. Okay. So, so you will see that your Lindstedt Poincare technique essentially what it does, it solves only the periodic solution. But on the other hand, your multiple scale MLS, it can also solve non-periodic equation. Okay, so this is your more powerful. Okay, that means what? If you have damping in your system, you will get a solution like this. Okay, but this is not periodic. So, but I think we can also verify it. Okay, so so if you simply do an analysis, okay, if you do a simple analysis like x double dot plus gamma x dot and x equal to 0, okay, and use Lindstedt Poincare technique and multiple scale technique on this problem, hmm, you will see that your Lindstedt Poincare technique, I mean, you can solve it analytically, but if you do Lindstedt Poincare technique, this is a lengthy exercise, but you will find that your Lindstedt Poincare technique is giving you incorrect answer. Okay, but multiple scale technique agrees with the you already have the analytical solution. You can find the multiple scale technique, and the analytical solution gives the multiple scale solution, and the analytical solution agrees with each other. Okay, okay. Now, option 7. Okay, so now it says that for the if you have equation like this, we have already solved this equation. 0. If you have this equation, then straightforward expansion like x equal to cos t plus epsilon x1 plus dot dot, it will not work. Then why? Why it will not work? What we are saying, I mean, we are. What so far what I have told you, I have told you that on the right hand side you will get cosine t or sine t, this kind of term. All right, but that is just a mathematical expression that is what you get doing at the time of when you are doing the mathematics, but that is not any physical answer, right? So what is the possible physical explanation for that? When you have this and you are adding something, sorry, when you are trying to solve this using the regular derivation technique, it fails generally. It doesn't work. But what is the physical reason for that? Remember that x double dot plus x equal to 0 is, suppose you are consider the pendulum problem. Okay, this equation will represent the equation of a pendulum. Okay, when your displacement x, this is very small. Now you have added something else plus epsilon x cube. Remember, what is the series expansion of sine x? Okay, before the series expansion, what is the original equation of this pendulum? It will be x double dot plus sine x equal to 0. And what is the series expansion of sine x? Sine x is x minus x cube by 6. Okay, see, x cube is there. So when this equation is true, this equation is true everywhere. But if your x is small, this equation is true. If your x is large, this equation is true. Now, adding a term x double dot plus x plus epsilon x cube equal to 0 indicates that your x is no longer small. Your x is large. So this is your pendulum for small x. This is your pendulum for large x. And you can try it yourself. If you give it a small perturbation, okay, the frequency you get from here, if this is omega s stands for small, and for this large perturbation, if the frequency is omega l, you will find that your omega l is greater than omega s. In the last class I have also discussed about it. It indicates that your frequency will depend frequency let's say this is a very important point, so let me just write it. Frequency will depend on initial amplitude. Okay, so your frequency will depend on your initial amplitude. Okay, so that's why. But here you see, here in the regular perturbation, you are just writing cos of t, that is coming from your natural frequency, right? Cos of t. So technique doesn't work here. Okay, now we have already solved this equation using Lindstedt Poincare technique. So here I haven't mentioned it there, but you see, yeah, you see that this term. So now if you just modify to omega, now what is your tau? Tau is your non-dimensional frequency, right? Tau is 1 by omega dimensionally. So you can clearly see from here, your frequency does contain a term which is coming from your initial perturbation. Here, what is a A is your initial perturbation. This is in your solution. Okay, A is your initial perturbation, and from the and the lean state Poincare technique does contain this information. Okay, so that's why it works. So this is the whole physical explanation that why your regular perturbation theory fails and why lean state Poincare technique or multiple scale technique works in this case. Okay. Okay. So let us solve the last problem of today's class. Okay, so let us solve the last question. Okay. So again the same problem. X double dot plus x square equal to 0. Okay. Now if you take the expansion like epsilon x1 plus epsilon square x2, then what will be your, and if you expand the time like this t into 1 plus epsilon omega 1, then what is the value of omega 1? Now we have already solved the problem from using the multiple scale technique, right? That from there we have find that del A del T1 is equal to 0. From the multiple scale technique we have found that. Now from that information and what I have told you about, okay, so from that information only, can you predict what will be your omega 1? Your omega 1 will be 0. Okay, because see what happened in the multiple scale technique, your x0 of t was some a1 t1 into e to the power of I t0. Huh? Now, if a1 t1 is some function of t1, if a1 t1 of e to the power I by 4 t1, it can be okay. It may be possible in some problem. In here in this problem, this is 0. So a is constant. So there it will be I into t naught minus t1 by 4, right? So what happened there? Your equation. So this is related to the frequency of the problem. So this equation gets modified. As a result, your frequency get modified. Okay, but if this is constant, if this is constant, so your frequency doesn't get modified. Okay, your frequency just is e to the power it, not e to the power it, right? Here also you see that, and also see that this is an implicit problem. So you just use your concept, whatever I have told so far, that this is the implicit problem. So lean state Poincare technique and multiple scale technique should give you the same answer. Okay, so lean state Poincare technique will also work here, and from the multiple scale technique we have found that your frequency doesn't get modified. Okay, and on the frequency modification term is what? Frequency modification term is omega 1. So if your omega 1, so if your frequency doesn't get modified, then what omega 1 should be 0. This is only the logical explanation, right? So from this you can just map lean state Poincare technique and the multiple scale technique for the implicit problem. Okay, but let us I will anyway solve this problem completely, okay, using the multiple scale, using the lean state Poincare technique. Okay, so 0. Now if you substitute in this expression epsilon x1 plus epsilon squared x2, so at linear order, So sorry, at order epsilon, order epsilon. What will you get? You will get x1 double dot plus x1 is equal to 0. Order epsilon and order epsilon square, you will get x2 double dot plus x2 equal to minus x1 square. But there will be one more term. What will be the term? So your tau is t into 1 plus epsilon omega 1. So this term is very easy to forget, okay? Because you can see this x1 square, you can very easily see. But remember that here is x double dot is not based on based on t, it is based on tau. Okay, so there will be one more term. So your d dt equal to d tau into d tau dt is 1 plus epsilon omega 1 d tau. So d square t square equal to epsilon omega 1 plus epsilon square omega 1 square d square d tau square. So now you just need to substitute it. Sorry. So what will be, so not here, sorry. So what will be the one more extra term? One more extra term will be minus 2 omega 1 d square x1 d tau square. Okay. So that will be your one more extra term. So it will, we will just write here minus 2 omega 1 d square x1 d tau square. I think I have made no mistake. Yeah. Yeah. So this is correct answer. So now, so this is the at the linear order. So I have already told it so many times. It is solution e to the a into e to the power I tau plus some constant cc. So sorry, not constant. The complex conjugate. Sorry. Now I have to substitute it, and the problematic term will appear on the right hand side. Okay, so I will just do the right hand side calculation. So it will be, so on the right hand side RHS equal to minus x1 square minus x1 square minus 2 omega naught 2 omega 1 d square x1 d tau square. So it will be minus a square e to the power 2I tau minus 2 omega 1. So it will be plus 2 omega 1 a e to the power I tau plus some constant, the complex conjugate term. So, so remember again, I am repeating it again because you are doing it for the first time probably, that we need to remove the secular term from the right hand side in order to get the physical solution. Okay, now the secular term is e to the power I term. So the coefficient associated with it has to be 0. This is 2 omega 1a. So omega 1a has to be 0. Now a can't be 0, right? If a is 0, then the solution is a trivial solution. So the only choice is omega 1 equal to 0. Okay. See, but from the intuition, we have already got this expression. From the intuition, we can say, because not from intuition exactly, but as we have solved the multiple scale technique, from there we can easily say that your omega 1 has to be 0. Okay. So okay, so just okay, so that was the last problem. So just for a brief summary, so what we have done today. So first just so first, that's what is the perturbation technique. So I have solved a perturbation an algebraic equation using the perturbation technique. Then we have changed our gear to the differential equation, because we will be solving differential equation in this course mostly. So there we have learned what is the regular perturbation technique, Lindstedt-Poincare technique, and the multiple scale technique. We have learned about the power. We have learned that about the power of these techniques. Okay, we have learned that the multiple scale is the most powerful technique, but this is the most complicated technique. Okay, the regular perturbation technique is the most easiest technique, but most of the time it will not work. Okay, so then there you need to use you need to use your listed pointer technique or the multiple scale technique. Also, you can do one to you can find a one-to-one correspondence with the between the listed pointer technique and the multiple scale technique if your system is invasive. If your system is viscous, okay, you can just do it. You can do it on your own. I have given you one problem. What was the problem? Okay, so yeah, so this problem, okay, you can try at home. You can use try to solve. You already know the analytical solution of this question. I have solved a problem today, which is related to this. So there was some if not sine omega dt on the right hand side. You just need to make that zero. So you already know the analytical solution of this equation, and and you try to solve it using listed point grading technique and a multiple scale technique. You will find that your multiple scale technique is giving correct answer compared to your analytical solution, but listed point grading technique fails to do that. Okay, because there is viscosity in the system, and listed point grading essentially works on the uh, periodic solution, periodic system. Okay, so we have learned the one-to-one correspondence between the listed Poincare technique and multiple scale technique. So, and we will move forward with this, and so now, okay, so just a moment. Okay, so so in the next week we will do some more complicated problem using the multiple scale technique, and we will do something called the Floquet analysis. Okay. Also, good night. And we will meet in the next week. So I will upload this video, this live session in my YouTube channel, and I will share these documents with you. Okay. So good night.